All right, well, good morning, everyone, and welcome. My name is Alex Desherbinen, and I am the chair of today's session on exposure. And it's the title, exact title is, excuse me, I'm scrolling up quickly. Population exposure to various climate hazards and the implications for managed retreat. So while many of the other sessions that you may have attended thus far focus heavily on the topic of local issues, working with communities, policies, buyouts, some of the very gut-wrenching emotional aspects of talking with communities about the potential necessity of relocating, and some of the mechanics, and of course the environmental justice and other issues. This session is focused more on the potential numbers of people that could be affected by things like sea level rise, flooding, storms. And it's important for, for planning purposes to have that information available and to know, how many people may be affected. And so I'm not going to do much more of an introduction than that, because we have an all-star cast here of papers representing really the state of the art and how to best ascertain the number of people who will be affected in the future, potentially under different scenarios. We'll also talk a bit about the potential for migration displacement from these different hazards in our talks. So with that, I will pass the baton over to Kit, and I'm looking forward to a very rich session. Thank you.
Thank you, Alex. So let me go ahead and share my screen. Can you see it okay?
Yes, we can.
All right, thank you. So my name is Kit McManus. I'm a GIS developer at a research institute at Columbia called Season, where I work with Alex. I spend a lot of my time doing data and application development work for the NASA Socioeconomic Data and Application Center, or NASA CDAC. I also am an adjunct at Columbia, where I teach some intro to GIS courses and some spatial analysis courses. Today, I'm going to talk to you about low elevation coastal zones. And in particular, there's two things I want to focus on. The first is, the sensitivity of data and why measurement matters, and why what we're using to create these zones and to add up the number of people in them has big implications for the results and what we'd want to do with policy. And then I'm going to take a look specifically at an application of these data to Deltaic regions. So, I get the honor of presenting on two topics here, because unfortunately some of my colleagues who were meant to present on the Deltaic information weren't able to make it today. So bear with me for a few more slides than you might expect, as I'll cover both of these topics now. So first, I want to look at how sensitive sea level rise exposure estimates or storm surge exposure estimates are to our choices of input data. And specifically, I want to look at different elevation data sources, different population data sources, and also different sources of settlement data along an urban-rural continuum. So classifications of settlement types. So it's useful to remember, I know in this audience, most of us probably know what a low elevation coastal zone is, but for those of us who might not, I want us to remember that LECZs, they represent zones of pixels that are coastally contiguous. So in future slides, I'll get in a little bit more to what that means, but we want these elevation pixels to be connected to coastline. So if there's some inland area where there's a very low elevation, like Death Valley in California, that's not something we want to necessarily include as a low elevation coastal zone. So the proximity to the coastline and the connectivity is really the key to what this term means. It's also useful to understand that the existing DEMs that are out there, they have root mean square errors in them. So, and they can be quite large. And, not surprisingly, these data, they're not stationary. So the amount of error varies throughout space. In some regions where, as Hawker, Neal, and Bates showed in their 2019 study, different elevation data products have better accuracy in various land cover types. So that, the TandemX elevation data set does very well in bare soil conditions or shrublands, whereas the Merit DEM product has better accuracy in short vegetation and tree cover areas. So like I say, the accuracy is not stationary. It varies between different land cover types. It varies throughout space. So many times though, when someone takes on a global analysis, we're constrained to use one data set or another. And therefore, we need to be mindful and be able to communicate the limitations of which data set we've selected and the reasons why we've selected one data set over another. So in this study that I'm presenting here, we looked at 4 different elevation data sources, and they were from the SRTM, which, most of us know that SRTM set the baseline and was really innovative in creating a global elevation model back around the year 2000. There's Merit DEM, which as its basis has SRTM data, but makes some improvements using altimeter data and validation techniques. Coastal DEM, which is one of the newer data sets that was just released in the past couple of years, also has SRTM as its baseline, but it uses machine learning techniques and different modeling techniques to make improvements. And then there's TandemX, which is a radar-based data set that is completely unique from SRTM. It doesn't use SRTM as its basis at all. So as you saw in the previous slide, Hawker showed that TandemX and Merit DEM, they have high accuracy in different land cover types. When it comes to population data, there's also a lot of decisions to make. The 4 data sets we chose to look at are the gridded population of the world, or GPW, GHS POP, which is based on the Global Human Settlement Layer out of the Joint Research Center in ISPRA, Landscan, which is a very popular data set out of the Oak Ridge National Laboratory, and then World POP, which is a very robust and popular data set out of the University of Southampton and the World POP and FlowMinder groups. When it comes to settlement data, we also had choices to make, but it's useful to note that there weren't as many ready-made products here, right? So there was a lot of raw data that could potentially be turned into settlement data, but we had to do some pre-processing in order to make that happen. So our data selection here was driven by the key requirements that we wanted to be able to identify populations within settled areas. So we wanted to know the urban population, the semi-urban population, and the rural population. And we wanted to be able to measure these settlements over time. So we want to answer the question, are the LECZs developing faster than the inland areas? So for settlement surfaces, we used one data set that's based on nighttime lights called DLight. So DLight uses DMSP information and also information from the more modern VIIRS sensor to create a time series of nights at light for 1992, 2002, and 2013. Global Human Settlement Layer built up product also is a time series. It's based on optical data from Landsat, and there's also versions that are based on Sentinel. The Global Human Settlement Model, or GHS SMOD, is a value-added product from the JRC, where they've taken into account densities as well of population as well as built up areas in order to create a thematic layer that classifies areas as urban or semi-urban or rural, or I believe that there's around 13 possible categories, but for our purposes, we reduced that to 3. And we also used the GRUMP data set as a basis for comparison to earlier work. So GRUMP data set was based on nighttime lights and regression modeling. It's one of the first data sets to create a global settlement layer. So we kept it in the mix in order to compare to those previous work. So I won't go into a lot of detail here, but I wanted to keep it in the slides so that people have access to it later. But here's what we did to turn these data sets into the 3 classes of interest for us, which were urban centers, quasi-urban center clusters, and rural grid cells. So for each one of these input data sets, we either had to apply some threshold, or we had to, in the case of GHS SMOD, use the methodology that the Joint Research Center pioneered in order to define these different categories. So inherently, these choices of thresholds have impacts on the output. So there's work that could be done in this domain to get the sweet spot in these. However, we do feel quite confident in what we've done here as a first pass. So this is just a summary of the data sources. Again, we had 4 elevation data sources, 4 urban concepts. GRUMP is not listed here, but the 3 main ones, GHS MOD, GHS Built, and DLight, and then 4 population data sets. As you'll notice, all of these data sets come at different resolutions. So we did do some pre-processing in order to harmonize the data. So some important notes on the methods. For our elevation datum, we used EGM 96. The only data set that wasn't natively in that projection was TandemX. So we used GDAL Warp and Python in order to translate TandemX into EGM 96 datum. The horizontal coordinate system we use is WGS 84. The resolution we selected was 9 arc seconds, which is approximately 250 meters. The reason why we selected this was because it enabled us to have a full time series to look at 1990, 2000, and 2015. I mentioned earlier this concept of coastal contiguity. So in order to determine coastal contiguity, we did take administrative data for coastlines, but because administrative data for coastlines is inherently uncertain, we buffered that data by 1 kilometer in order to create an inclusive coastline. And I'll show an image of what that is in a second. But to evaluate contiguity, we use this concept of image segmentation. And probably the thing people will like most in my presentation is this cat graphic that shows you what image segmentation does. Basically it takes an image and based on connectivity or similarity, it can segment it into different regions. So when we're looking to see if something's connected to the coastline, it needs to be regionally connected to the coastline. So this has some implications. So as I said, we buffered the coastline to include more area in the LECZs because that overcame some inaccuracies in administrative polygons. You see in this example here for Sri Lanka that in the left-hand panel, in the southwestern portion of the country, if we would have used the strict administrative boundary, there would be large areas not included in the LECZ that when we use the buffered coastline are included. So this is an important nuance to remember when evaluating our work. More on coastal contiguity. We saw from the Hawker paper that TandemX is very highly accurate. Globally, it's considered one of the highest accuracy data sets. But TandemX, it's also very heterogeneous. So, it's accurate, some might say to a fault, where it's capturing things like roadways, which you can clearly see in this top image. And because it captures these things, it can potentially lead to contiguity gaps, right? It can create barriers where in reality there may or may not be barriers. Whereas a data set like coastal DEM is very smooth. So, this is the same region in China we're looking at, and you can see in coastal DEM, it's not capturing the roadways, it is capturing agricultural areas, but it's very smooth, which leads to more contiguity to the coast. So I'm going to jump into the results. I realize that I'm short on time. I do have 2 sessions back to back here, and I will get through both of them. So the results in the nutshell, looking at sensitivity, this is land area in LECZs. And what we found is across the different elevation data sets that coastal DEM assigns more area at the 0 to 5 LECZ, and merit DEM assigns more area in the 5 to 10 meter LECZ. Some of the reasons for this is that heterogeneous or homogeneous, or the smoothness of the surface that I showed in the previous slide. But depending which elevation source we choose, you get a different size LECZ. When we looked at population, you see also here that there's a lot of variation in the population. Right here, we're looking at the percentage of the population in up to 5 meters, 5 to 10 meters, or above 10 meters. But one thing that's consistent across these estimates is that the GPW data set consistently estimates the lowest percentages in low elevation coastal zones, and GHS POP consistently estimates the highest percentages. We found that estimates are more sensitive to the choice of the DEM than they are to the choice of population, even though there is quite a bit of variation here in the population data within any given category. So along the urban continuum, we found that when you use GHS POP, it concentrates more people in urban and quasi-urban areas, whereas GPW tends to concentrate more people in rural areas. And that the settlement estimates, they're highly sensitive to your choice of input data. So if you want to create a dichotomy of urban or semi-urban and rural, the choice of your input settlement layer makes a big difference. And then the population data you use with it also makes a big difference. So you can end up with a wide array of different estimates. So when we look at changes over time, though, we find that urban areas have experienced the greatest increase in population, and this is no matter which data set we used. And no matter which data set we used, we found that urban areas inside the low elevation coastal zone have grown even faster than those outside. So there are some important limitations to this study, namely that the LECZs are a static measure akin to bathtub modeling. So they're not a dynamic measure. They're really just based on the physical nature of elevation. And also there's limitations because we don't know about connectivity. Things like culverts and underground infrastructure, they're not incorporated into our contiguity modeling. And, as we stand here in 2021, data on contiguity, even in New York State, where I'm from, it's very hard to get. It certainly doesn't exist globally. And in most cases, it doesn't even exist nationally. So we do need local studies in order to improve on this. And, ultimately the goal is to create connectivity data sets for larger regions. But that is a limitation of what we've done. So some of the take-home messages of this study is that data choices can lead to large differences in estimates of population. Users, they should consider fitness for use for their specific use cases. This isn't something I've discussed, but in the paper, there's a large discussion about fitness for use. So I'd recommend people take a look. And despite major differences, every source we evaluated showed that LECZs are disproportionately urban, and that the urban population in the LECZ is growing faster than outside of it. So to continue this discussion, there's a preprint of this work available on ESSD. I will put this in the chat when I get a chance to. So we welcome community comments. It's open for comment at this time. So I'd be happy to hear from you there, as well as later in this talk. So I want to move on to part 2, which is a case study looking at Deltaic populations at risk. So since we've established that the LECZ is disproportionately urban, we want to know where are the most people. Could it be, could it be that administrative data like countries aren't really capturing that, and maybe we need to use an alternative geography like a delta? We also want to know over time what's changing. Are these deltas growing faster than other areas? The results that follow, they don't have the full spectrum of those 12 different data sets, but they do include elevation from Merit DEM, population from GHS POP, and settlement data from GHS SMOD. So here we see there are regional differences. In this graphic, the black lines are 1990 and the colored bars are 2015. And we see specifically that population growth in the Asian LECZ is disproportionately in urban areas compared to other continents. When we look by continent, we know that cities are at risk everywhere, but once again, we're seeing that in Asia, the 0 to 5 LECZ is the most at risk. There just happens to be a lot of large cities that are situated in these Asian deltas. And you can see that over time, it's growing even faster than outside the delta. So we want to ask how much of the LECZ is deltaic. So globally, if there's 815 million peoples residing below 10 meters in 2015, about a third of them live in the deltas. So of the respective proportions in the 0 to 5 meter zone, it's on the rise in deltaic regions, and the proportion of POP in the 5 to 10 meter zone is growing both inside and outside of the delta. So here, we have some images that show 1990 and 2015, both inside and outside of deltas by 5 meter and 10 meters. And you can see that it's growing everywhere, but faster inside the delta in the 10 meter LECZ. So in the 10 meter LECZ, the deltas and their overlaps, there's population densities and growth rates. Again, we're seeing that inside the delta, there is a greater density, both inside and outside the LECZ, and that inside the delta, there's faster growth than outside of it, whether you're in the LECZ or not. When we look at this in terms of built up area instead of population, we see a similar pattern emerge, that if we look at the shares of land area built up inside and outside of LECZs and deltas in 2015, there's more built up area inside the delta than outside of it. And that's regardless of whether you're inside or outside of the LECZ. But if we look at growth rates for those same time periods, we see that the growth inside the LECZ, so this is how much more buildings there are, how much more built up area, is growing faster inside deltas, inside the LECZ than anywhere else. So we want to move towards a better understanding of the deltas. Particularly we want to understand the growth of urban areas in the LECZ in Asia. For this, our choice of data matters. Different data combinations, as we showed previously, they can show different results, but there are some similarities. And one thing we need to understand is whether or not the elevation data is distorting some of the results by capturing things like high-rise buildings as higher elevations. So I think I finished just on time, and I can't believe I did. But if there's any questions, I'm happy to take them in the session here. Also, my email is here, and I will join the chat and put some links in there soon. So thank you very much. And Alex, I can turn it back to you.
Thanks so much, Kit. That was a real tour de force and extremely clear, I might add. So thank you so much for that very clear explanation of some of the methods required to get accurate and I would say some uncertainty bounds around the estimates of people living in the coastal zone and in urban areas in the coastal zone in particular. So thanks again. I think next up is Cascade, if I'm not mistaken. I'm just pulling up yes, Cascade. Too hot to handle, a global analysis of urban extreme heat exposure trajectories. So Cascade, over to you.
All right, thanks, Alex. I'm going to share my screen. All right, are we on the full view? Not hearing anything.
Yes, you're fine.
Yes.
All right, cool. So thank you for being here this morning, this afternoon, this evening, wherever you are in the world. I'm really excited to present. My research, as you'll see, it's not an inner comparison to the extent that Kit's presentation was, but essentially I'm doing very similar analysis where the hazard we're looking at is extreme heat events. Mine is a historical analysis mapping the trajectory of urban population exposure across the entire planet to extremely hot humid heat for the last about 35 years. This work has been a long haul, and I'd just really like to thank my co-authors at UC Santa Barbara and University of Arizona and University of Minnesota. Could not have done this work without them. The United Nations projects that the planet will add 2.3 billion people to urban areas in the next, I guess we're in almost 28 years. The majority of them are projected to be low income, to be poor, essentially. At the same time, a huge body of research has shown that climate change is driving an increase in the frequency, duration, and intensity of extreme heat events. And these heat events can be lethal. There's a wonderful paper, I think I gotta adjust my screen a little bit. Oops. There's a wonderful paper by, I think it's in Nature, that looks at, it's both a lit review and a meta-analysis of every documented extreme heat mortality event, and then they go through a climate reanalysis product and look at the relationship between those fatality events that are documented in the academic literature and the average daily temperature and the average daily humidity. And there's this, while there's not always an exact threshold that will lead to fatality, heat and humidity kill. At the same time, at present, we don't really have an understanding of where urban population growth is intersecting with urban extreme heat. We don't understand where the signal from, I'm going to say, total urban warming, because there's also contribution to, I guess, we're calling the twin forcing agent between climate change and the urban heat island effect. We don't really know where total urban warming is intersecting with population growth. And where it's not. And I think that has some pretty strong implications for how we divert or use limited resources to adapt to extreme heat and urban settlements across the planet. In my analysis, I'm using a new daily temperature maximum and relative humidity product. It's the temperature product's called Church Daily. And basically, it relies on a high resolution monthly climatology that blends station data with satellite, meteorological satellite observations. And then it bias corrects the ERA5 climate reanalysis product at 0.05 degrees, which is higher resolution than any other temperature, daily temperature record to date. It's also shown to be more accurate than ERA5 in measuring extreme heat days, and more accurate correlation with station observation with other data sets like the Princeton Global Forcing data set. I am thankful for Kit because he presented the global human settlement layer. There's also another auxiliary product where they basically take those population rasters and the settlement classification rasters, and they use a smoothing algorithm to isolate actual urban settlement polygons. So it kind of cuts out a lot of the noise, and all those polygons are assigned an actual a name and a country. And so we have a rough idea of the populations and the locations and boundaries for 13,000 urban settlements going back to 1975. So what I do here is in the Church Daily data set is I've created the wet bulb globe temperature, which is extreme heat measurement that accounts for humidity and temperature. And I'm using the International Standard Organization's definition for extremely hot heat stress, or extremely high likelihood of heat-related illness, which is wet bulb globe temperature max of 32 degrees Celsius. So I go through the whole record, I find all the days where that happened, I total the number of days per year, and I multiply it by the number of people exposed, so for each city, and then I regress the trend line. So my metric here is person days. So this data set contains that I've produced 150 million daily urban temperature exposures to this threshold. And then these points map those trajectories. Dark red is a steeper trajectory. As you can see, basically low latitude urban settlements have the strongest, or I guess the steepest slope in the increase in exposure. But if we just look at the number of days per year and the regression of that, a slightly different pattern emerges. And you see that there are some cities or urban settlements on the planet that have, for the last 34 years, a 4 days per year increase where the number of days per year exceeded wet bulb globe globe temperature max of 32 degrees. So 4 times 34 is about 200. So some of these cities are reaching a point where they're saturating, where every day per year may exceed this extremely high heat threshold. But in this data set, there's a lot of spatial heterogeneity between the urban warming signal and the population growth signal. So you remember our exposure metric is population times days per year with wet bulb globe temperature greater than 32 degrees. So if you hold population steady, you can look at the signal from just total urban warming, and vice versa. You can look at just the effect of population growth. And what's really striking about this data set is that even in regions with rapid urban population growth, the urban warming signal as a contribution to total exposure is coming through as stronger. So southern India is an area of concern. Cities are growing really fast there, but the urban warming signal is growing even faster in terms of the contribution to total exposure. As well as the Tigris-Euphrates region is another area of concern where that warming signal really comes through in our data set. So just for 2 very specific cities about why geography matters, especially in terms of thinking about adaptations, early warning systems, and interventions. Delhi and Kolkata have largely similar exposure trajectories. So in panel A, that's the growth and exposure for those 2 cities over the last 34 years. And they're largely similar. But if you look at the effect of total population growth in panel B versus the effect of total warming, they kind of flip-flop. So in Delhi, the signal from population growth is much stronger, whereas in Kolkata, the signal from total urban warming is about 50% of the contribution to total increase in exposure. And so this kind of analysis can be done for all 13,000 cities I have in this record we've built. And I think this is really important for practitioners to start understanding where which cities one may be getting to the point where at least for certain times of the year, these cities will be literally too hot for humans to possibly live in. But that the contribution to the exposure can be driven by both demographic and I'd say human change to the urban environment and climate change. So with that, I'm going to stop. I really welcome any questions. This paper should be published hopefully in the next couple of weeks, and I'm really excited to share this data set through NASA CDEC, hopefully, and through Season for anybody to use. So please feel free to follow up with me if you have any questions. Thank you.
That was terrific, Cascade, and an extremely crucial issue. Especially as you think trends are undeniable. Abby, I'm going to ask you, were there any questions in the chat that we should take now, or shall we keep going ahead?
Go on ahead.
Okay, thanks, Abby. So this, we're going to continue our rapid fire. We have a large number of presentations in this session, but we hope to get to more discussion towards the end and maybe some exchange across some of the different type of threats that we're exploring here. So the next presentation is by Beth Tellman, a colleague here at the Earth Institute, but now moving to University of Arizona. We're thrilled to have her speak about flood risk. And so over to you, Beth. Thank you.
All right, thanks, Alex. And I think you'll hear in my talk a lot of echoes of what Kit talked about and what Cascade talked about. So I'm really looking forward to the discussion for us to dig in, because I think we're using similar kind of data sets, looking at different hazards and finding some real trends here and where and how development is happening around the globe and what that means for adaptation in a climate changed world. Let me minimize the video here. Okay, you can see my screen?
Yep.
All right, great. So I'm going to share with you some recent work that is coming out, I think in maybe 2 or 3 weeks. It's in press now. We've been working on this data set for a long time, and we're really, really excited that we're finally going to be able to release it. This is a project funded by Google Earth Engine in collaboration with the Dartmouth Flood Observatory, and I've been working for a long time on this data with a company that I co-founded called Cloud to Street. So if we think about how do we normally measure exposure to floods, or the typical ways to do that, it's typically happen in 2 ways. One is through disaster database statistics. Folks here maybe have used MDAT or Disinventar. The problem with those are that they're mostly reports either by governments or the media. So they're really inconsistent. They're spatially coarse at large administrative units. They're often really biased because countries report and even define who is flood affected in different ways and what does it actually mean to be flood affected. You know, you could have your crops in a certain area or your road access shut off. And so sometimes those numbers can get much higher depending on, you know, who's reporting and what their definition is. The other way that exposure is typically assessed is through flood models. So this is, you know, big computations trying to produce either footprints of flooding of historic events or the probability of a flood happening. But those suffer from really, really high uncertainty. Here's one example of a recent study that compared, this is here like 10 commonly used global flood models. And depending on which one you use, either 20 or 40% of China's GDP is exposed to the 500-year flood. So that's a massive kind of difference in distribution. So again, echoes from Kit's presentation on, you know, what data set you use might really affect your answer of who's affected and where by a hazard. And we need to think through those issues. When you stack up 6 large global flood models together in sub-Saharan Africa, this is work by Mark Trigg, again, you find massive disagreement in where flood model extent actually is. But if you actually check out a satellite image of a flood event, here I've zoomed into the Eastern Nile Basin, in blue, you see where the flood happened is actually pretty different than where models said the water was gonna go. Why is that? Because humans adapt to hazards. We build levees and infrastructure, and we channel where floodwaters go. We grow cities, and that might increase flooding in some places. And so what satellites really help us do is, instead of just estimating the probability of where a flood could occur, we see where the water happened, where a real flood occurred. And because the satellite record is getting longer, more frequent, we're increasing our spatial resolution, our ability to do that is getting better and better. And we could leverage that for better exposure estimates and give us some more information about what's going on. So what we did in this project is kind of the first global attempt to do this consistently. We used the Dartmouth Flood Observatory data. Some of you may have used this. And this is an incredible effort by Bob Breckenridge since 1985 to catalog systematically large flood events around the world. But some of those events just had a point or kind of a rough polygon associated with where it happened. So we thought, let's map every event consistently using MODIS, which has 2 images a day in Google Earth Engine for computation, and get as many floods as we can from their archive at a 250-meter spatial resolution. Of all of the floods we tried to map, we think we got high quality events for 913 floods at a reasonable accuracy. It was note 2 caveats here before I dive into results. We only mapped a third of large floods, so we're mapping large, slow-moving events, often where clouds are clearing. Often we were blocked by clouds. Flash floods where the water moves too fast, we cannot capture. Urban floods where water moves at high spatial resolution, we cannot see. So again, this is a biased sample of very large, slow-moving events. Nonetheless, it gives us a lot of information about where we've observed water in big events around the world. And we're gonna dig in and see kind of what we find in what we did see. So we capture, here's kind of a sample of large events of the type that this database captures. So the highest mortality event in the database, Cyclone Nargis, 100,000 people killed in 2008, that's panel A. You may recognize New Orleans here in panel B. And we have like a really large exposure event from the 2007 floods in India and Bangladesh, and a really long-lasting snowmelt flood event in panel D. These are the kind of events that we capture in this database. And when you zoom out and look at it globally, what we found, and again, I'm not getting into the weeds here, but to kind of go back to Kit's presentation, we present ranges of population data because we use both GHSL, kind of the GHS pop data set that Kit talked about for population exposure, how many people live in each pixel that we observed as inundated in these events. And we also used HRSL, the high resolution settlement layer, which is not available for every country, but we were able to look kind of the bias difference between those 2 data sets. Turns out the higher population resolution data you use, you typically count more people flooded. So it's important to kind of think about this number as a range. The truth probably lies somewhere in between this number of 255 to 290 million people that we found exposed to at least one flood event in our database, and a lot of concentration of events in Southeast Asia. Looking at the type of events, there's a lot of, most events are driven by rain, but you can see some coastal events we have in here, snowmelt, and importantly, dam breaks, which I'm going to talk about in a minute. So when we looked at each of these different events and the population movement in them, we took the data from GHSL and we looked at how many people were living in a place that we observed as inundated in the last 20 years, in the year 2000 and in the year 2015. And do we see movement in and out of floodplains? And we saw so much dynamism here. Places like New Orleans, where we know after Hurricane Katrina, a lot of folks affected were unable to rebuild and left that inundated area. And we see population decreasing there. Places like Dhaka, I think Kit talked about this, in Guwahati, India, that we know are growing into places that we've observed as flooded. Dhaka, there are so many homes being built in places that flooded just as recently as 2007. Other places like Manaus, Brazil, where we didn't really see that much change and where people were moving in and out of the observed floodplain in the satellite record. Just to kind of contextualize what this means, when we measured how fast is a country's population growing versus how fast is the population growth in the places we saw as inundated, we found something I think somewhat shocking, which was that flood exposure is growing globally 20 to 24% faster than population growth. What that means, and this is kind of the art to illustrate this point, is that people are building more in places that have been recently exposed to floods than places that are not, writ large at a global scale. A lot of that is concentrated kind of in these orange and red countries in sub-Saharan Africa and Southeast Asia, but that's a really like difficult development trend. What we see actually is that in places like the US, many countries in Europe, and in more Eastern Asia, that there are actually land use zones and policies in place that try to prevent people from rebuilding in places that were flooded. In some cases, that maybe is a good thing, that those development trajectories are not continuously expanding in the floodplain as much as they're expanding in other parts of their country. So land use, adaptation, regulation matters. The last thing is that kind of important to note, this rate of exposure growth that we found is 10 times what previous studies have predicted that use flood models for exposure. So if you use satellites to understand exposure, you're going to get a different answer than if you use models. And we should maybe lean into that and work more on using satellites for direct exposure in the future. Another really shocking trend is that where we found population growing the most was in these dam break flood events. So hydrologists call this the levee effect. So what often happens is we build levees and dams and infrastructure, and then people feel safe. Land values go up, people start moving into the floodplain. But if that dam isn't kept up and it breaks, it's devastating. This is an example of one such devastating event where thousands of people died in 2008 in Kosi, India. This is really important for us to keep in mind in the US as we think about Biden's infrastructure plan. It's really important to upkeep infrastructure. We have a lot of aging dams in the US, and they do sometimes break. We have several dam break events that we've mapped here in the United States that are just devastating. If we think about what's going to happen in a future climate, we have to use models here because we haven't observed it, obviously. So lots of uncertainty with these estimates. But we find another kind of shocking result, which is that places like the United States and much of Europe, whose policies in the past may have been able to mitigate some population growth in the floodplain, won't be able to do that anymore because the floodplain will probably expand so much in a changing climate that that trend is going to flip. So we've got a lot of work to do to think about how to adapt our land use and zoning policies to reduce exposure and think about adaptation in the floodplain and how and where we want to build our societies. So the last thing I'll say, I was going to show this kind of interactive website we built, but I think I'm out of time. But I just want to let folks know that we'll be publicly releasing all of this data. We've got a really cool website where you can download any flood map in our database. You'll interactively be able to sort of click on different data, look at dates, pick different countries, and explore the exposure statistics that we have and the precipitation data we have for all of these flood events that we hope will be useful in your work if you work on riverine flood exposure. And that's what I wanted to share today.
Could you put that tool URL in the chat on the portal? So where the session portal, you can find the chat and people could find their way to that. That sounds like a really excellent tool. And thank you so much for your presentation.
Yeah.
Now, I'm going to try to keep to time myself as I present my work. And let's see if we can do this seamlessly. So apologies, I didn't get to the right page here. And if you want to shut down your video as well, Beth, that would be great. Thank you. My name is Alex Sherbin, and I'm presenting on behalf of a number of colleagues. And I just want to go through this relatively quickly. Some of you may be aware of the work that we did with Brian Jones at CUNY and colleagues, of course, mine at Season at Columbia University, and also the World Bank, primarily Kamari Rigaud and David Malecki on Groundswell. I've actually heard Groundswell being referenced during this conference as being a catastrophist view of the world. I don't take that view necessarily. What I think Groundswell offered the opportunity to do is to model at scale potential future shifts in population in a way that allowed decision makers, because the World Bank has the attention of decision makers in country, to really consider what that may mean for their planning purposes. So, the purpose is to support a constructive dialogue on human mobility. And for that, I think it's been highly successful. I do not believe that the countries that received the reports of Groundswell or have, had country-specific analyses necessarily took this as destiny, but rather took it as potential outcomes as a result of future climate impacts. In a very brief nutshell, the way that Groundswell works is to use 4 different scenarios that are combinations of development on the x-axis and emissions on the y-axis. The pessimistic scenario has both high emissions and inequitable development outcomes. And the optimistic, is down here in this corner, and it has relatively lower emissions and more inclusive development outcomes. For each one of these scenarios, we use 4 inputs from the ISIMIP, Intersectoral Impact Model Comparison Project, combined with different GCMs to model future impacts on the water sector, on crop productivity, and on net primary productivity in this new work that we did with the World Bank. So what I'm describing in essence is an enhanced Groundswell model that we applied to West Africa and East Africa in the last 2 years. So you run essentially a gravity model of population distribution into the future. It's calibrated on past changes in population distribution and their sensitivity to some of these same impacts. And you look at how population shifts may occur, and population migration is estimated based on the difference between scenarios that include climate impacts and those that do not include climate impacts. So we call it the climate impacts versus the no climate impact scenarios. If you subtract one from the other, you in essence get a difference, and we assume that that difference in population distribution is due to climate migration or migration. So we produced each country separately. We did not try to make any estimates about future bilateral flows between countries. Those were retained from the SSP scenarios. I do not have time to get into the SSPs, but there's a rich literature on that if you'd like to learn more about what the shared socioeconomic pathways represent. So what I'm presenting here is work from Groundswell Africa report, which is due out in 2021. This includes some enhancements on the original Groundswell report, which was published in 2018. You can go to the World Bank website and download the Groundswell report if you're not familiar with it. In that, those enhancements include higher spatial resolution and temporal resolution in our modeling steps and in our modeling resolution. So we went from 15-kilometer grids to 1-kilometer grids. It includes new layers such as impacts on net primary productivity, which represents essentially pastoral zones in West Africa, mean age or median age, and conflict in other layers that give a more nuanced picture of what may happen in West Africa. I'm going to just describe the demographic context very briefly, which is one of very rapid population growth with a large youth bulge at the bottom. And the population distribution, where a lot of the population is in fact concentrated along the Guinea coast here and the Cape Verde Peninsula of Senegal here. And there's a lot of urbanization. Urbanization rates are roughly 4 times the levels of the population growth rates in each country. The sea level rise estimates were very crude. So this is not an area where we did a lot of nuance like what Kit described in his earlier presentation. We simply used 2 very crude estimates for future sea level rise, one of 1 meter by 2050 and another of 2 meter by 2050. These include things like storm surge, and they're trying to capture not only the effects of actual flooding or inundation, but also things like coastal erosion, wave action, saltwater intrusion in aquifers, and things that we know can affect the livability of locations in the coastal zone. We also know that a lot of urban areas are in this low elevation coastal zone. I'll just mention briefly that Season did some modeling in 2010 and 11 for the Foresight report on global migration and global environmental change. And if you summarize the results of net migration in the region from 1970 to 2000, roughly 10.6 million people left out of the dryland areas during this period, and 9.2 million people went to the coastal ecosystems, 6.6 million of which moved to the low elevation coastal zone. So here are the time steps in our progression of the model results for that work. So what we know from research findings is that, in fact, coastal areas are still typically areas or locus of in-migration. People have not really yet registered the impacts and decided yet to move out of these areas owing to the impacts. The DECMA project, for instance, found that in the Volta Delta, communities essentially accept the risk for greater perceived advantages of living in that Delta area, maybe higher soil fertility, maybe greater opportunities for commerce. It's certainly more centrally located on the border between Togo and Accra. So there's a lot of reasons why people choose to live there. Yet, that said, in Saint Louis and a few other parts of the West African coastline, resettlement is underway. So in Saint Louis, some of you may be aware that there's a World Bank funded resettlement project away from the coast. This was partly a man-made disaster. So it wasn't purely sea level rise, but there was major flooding of the Senegal River about a decade ago, and they actually blew a hole in the sandbar to relieve the pressure from the floodwaters to protect Saint Louis. As a result of doing that, they actually changed the morphology of the coast, and it resulted in much higher levels of erosion than before. So there's a lot of displacement in that area. So at a regional level, if you look at the hotspots map, as we call them, these are maps that basically show the agreement of across the 4 scenarios, the level of agreement. So the high certainty means that all 4 scenarios suggest that there'll be at the top 10 percentile of in or out migration from these areas. So these tend to be more densely populated places in the first place. The red areas are in migration hotspots potentially, and the blue areas are out migration hotspots. And what you see is there is a lot of potential out migration going to occur along the coast in Nigeria, Senegal, and Ghana, and some other areas, Abidjan as well. What should be stated though up front is that this does not mean that these areas will depopulate. It simply means that compared to the development only or shared socioeconomic pathway only scenarios, climate change will attenuate growth in these areas, and you'll see maybe lower growth than might be expected in a development only scenario. These changes in population distribution largely mirror what we project will happen with 2 major drivers, which are water availability and crop production, as well as the sea level rise mass that I shared earlier. And so what you see on the left is a map of deviations in water availability in the Sahel and in all of West Africa. In red, lower in the future than the past, blue, higher than in the past, and the same for crop production on the right. So I'm going to basically run out of time to go into details on each of the countries. This report will be out in the next couple months. So you can look for it on the World Bank website or contact me. In Ghana, what we see is future outmigration to sea level rise and changing water availability in the south projected. This is sort of a zoom in on Accra. And the line charts on the left show the levels of outmigration that we would expect from these coastal areas in Ghana. And it goes up to about 150,000 persons may depart by 2050 from the coastal zone. Senegal, much more water deficit issues in western parts of coastal Senegal. This is going to exacerbate sea level rise issues, and we see potentially up to 400,000 people potentially leaving the coastal zone in Senegal, but with a high bands of uncertainty around that. think I'm going to end, but they really are intended to represent conversation starters in these countries. The Groundswell data will soon be available from NASA CDAC, so keep your eyes out for that. And with that, I will stop sharing and we will go to our next presenter, who I think will have a very similar message, which is Andrew Bell. And they've done some really excellent work in doing agent-based modeling in Bangladesh. And I think the story or narrative of growth of population in the coastal zone is somewhat similar. Andrew, over to you.
Thank you, Alex. And I'll try and keep to time and be quick. So as Alex said, I'm going to present a bit of an agent-based model, which normally I spend a bit more time situating and explaining, but very briefly in an 8-minute talk. Agent-based models are great tools for problems where you believe that the system level property you're interested in is strongly shaped by interactions and heterogeneity of individuals and groups within your system. And so I'm going to present a bit of a model called MIDAS and an application to Bangladesh that came about as part of a big succinct pursuit led by David Rathall and Valerie Mueller over the last couple of years. So very briefly, the motivation in building this particular model, we have a very long history of modeling migration in particular, going back more than a century, with a lot of the origins of this modeling being gravity models, which have grown into things like the Groundswell model. And the thing about them, and they're very powerful, wonderful for getting at global scale measurement, but they have places as a unit of analysis and not people. And what that means is in many cases, we miss this ability to capture that important heterogeneity and the complicated stories of why people move. People differ in resources that they have, aspirations, they differ in how they perceive things around them, they differ in their risk preferences, and we can't capture that unless we move to people as the unit of analysis, which we're really now well situated to do. We have more than half a century of strong demographic theory that places people as the sort of central unit looking at migration. And today, I think we very well understand livelihood strategies as emerging of sort of simultaneous calculus of a lot of different things. One of the theories that embodies this well and upon which a lot of MIDAS is based is the push-pull mooring or PPM theory. So very, very quickly, the basics of MIDAS and what it does, we have individual agents located in places, embedded in social networks and sharing information, sharing resources, and deriving utility from different sources in the place that they are. They're periodically making decisions about what is the best sort of portfolio of options for them. And if it's the case that that best portfolio is somewhere else, then they'll move. And so key features of this approach are that it allows sort of simultaneous consideration, simultaneous calculus of these different push, pull, and mooring factors, which you may see in other agent-based modeling approaches to migration, but often not simultaneous. So MIDAS is one of the earlier models to do this. And it allows migration then to be this emergent strategy rather than something that's kind of baked in and decided in advance, which I like. Now, a couple of key details, things that we can get at that end up being important. So for instance, here, agents pay for the ability to access different things, much like you would pay to certify as a teacher or a lawyer or buy an asset that you need to run a business. And they differ in sort of that degree of social capital, human capital, and their ability to access credit. They build different expectations over time for how they expect things to play out for them, and they build in expectations around variation, shocks. And as well, things like they learn what job markets are. They learn a little bit about the likelihood of their being able to move to a place and be able to enter that particular portfolio of opportunities that they're so excited about. And so they have an expectation about how likely that is. These are some of the things that are comparatively easy to do with an agent-based modeling framework. So the application that I'm going to show, entirely making use of secondary data, this is what we had available to us. We had a few waves of a repeated cross-sectional household income and expenditure survey from Bangladesh that was representative at the district scale. We had a partially overlapping annual data set of internal migration in Bangladesh between districts. And then we had sort of modeled projections at the decade scale for expected sea level rise under different RCPs. And I think we used 2.6, 4.5, and 8.5 in our data set. So really quickly, the workflow that we applied to pull all this stuff together was that we calibrated a MIDAS application by building a little kind of income model based on that HIES data and calibrating that to our internal migration outcome data. And then we took our flood depth projections to simulate what we expected to be kind of the worst flooding depths in a year, moving out through 2050 through 2100. And then we did the best that we could. We found, or we had access to, historical analog data for the impact of flood depth on agricultural and non-agricultural wages. And we used that as sort of a transfer function to interpret this expected future path of sea level rise, which we'll acknowledge is not the same as sort of historical monsoon or riverine flooding. But it's the best that we have. And we make an assumption, because we don't know any better, that the economy will stay the same moving out in the coming decades as it has over the few waves of data that we have from the HIES. And so we use our sort of transfer function to scale those wage opportunities based on changes in flooding. And then we look at what that implies moving all the way out into 2100. Okay, so we're making use of the sort of best available current secondary data and linking things together in the way that we can. We find some interesting things with the particular set of assumptions we've made. We see that, again, in this model simulation, the impact of those floods on wages reduces, but does not really fully suppress migration towards the coast under any of the RCP scenarios that we're looking at. So some of this, to the extent that the 3 waves of HIES data that we have embed any of this levee effect that was just mentioned, we're seeing that carry through, and we're not assuming that any of that changes because we don't have a basis to do so. But we're a little bit stuck, and I'll sort of wrap up in the next slide or two with things we don't know. I think I like this paper for us being able to say, look, it's likely that when things go underwater, people leave. But this is a plausible set of stories, and again, we're limited in the data sets that we have. But here's a plausible story where this doesn't happen. We've heard today of the kinds of drivers that are currently still encouraging people into coastal zones, and so I like this particular analysis for kind of poking a hole in the sort of really dominant narrative that everyone's going to leave when things get really, really wet. So it's worth thinking through. Now, having said that, the things that really strongly drive our findings are the ability to access credit, and as well the degree to which the experience of a SLR-driven flooding is experienced as a shock rather than a norm. And this matters a lot, and I'll sort of finish by kind of walking through the things that we don't know. So we play around in the paper, and I'll show a link to it in a second, with a couple of different credit interventions, but we don't really look broadly at the kinds of things we might expect national or international policy to do over time. We don't have a basis for that. We also don't know how economies will change. We don't know how infrastructure investments will change, or where big businesses currently operating in the coastal zone might move to. We don't know any of that. We don't know what the experience of SLR will be, and how it will be different, how it will be close to the history of experiencing monsoon and cyclone driven flooding damage. And importantly, and related to this, we don't know how a flood that's initially experienced as a shock then becomes the norm. And this matters because it's the difference between uncertainty versus expected variation. And we've all now just lived through this 1.5 year experience, this huge shock to the way we went about living our lives that we've gotten used to. And I would imagine for most people, it's still not perfect, and things are difficult, and we're coming out of it as different people, but we adapted. And it took a different amount of time for different families in different places. And this challenge is knowing what are the rules about the pace at which, again, people get used to things is really critical in being able to understand how things like this, any kind of climate hazard for which we don't really have a lot of good historical analog data is going to matter. We need to figure out some way to measure this. And so this is kind of a set of things that I'm just kind of loosely calling out of bag problems that just make it difficult to do really good, future projections on what we think people might do. So I'm going to stop there so that I stay in time. But if there's any interest in this beyond what I can say in 8 minutes, this is the paper. You can Google it. And if there's any interest in maybe extending this application or playing around with it or doing an entirely different application, I'd be really glad to talk. This is my email here, and I'll stop there.
Thanks so much, Andrew. The fascinating work, and maybe if you could put the link to the ERL paper in the chat on the attendee hub, that would be terrific, so people can find that. And I think Charlie is here, so we're going to go ahead and go direct into Charlie. Charlie, if you could keep it to about 10 minutes, we'll see if we can, 10 or so minutes, we're going to see if we can get some Q&A. We have a number of questions in the chat that we're going to try to attend to. So thanks, Charlie. And if you could switch presenter mode from presenter to the other mode, thank you.
Is this does this look right, Alex?
That's right. Thank you.
Okay. Alrighty. I'm Charlie Hike. I'm at a company called ImageCat, one of the founders here. We've been around for about 20 years, founded on the basis of trying to integrate GIS and remote sensing into the area of CAT modeling, which was sort of dominated by the engineering field at the time that we started. So CAT modeling is for insurers and governments to try to sort of figure out what might happen after an event or what might happen probabilistically, given all events, to set insurance rates and have planning scenarios and so forth. So one of the things that we did early in our history was the 4-to-1 study, it's known as, for MMC, Multi-Hazard Mitigation Council, where we assessed the cost efficacy of mitigation efforts. And as an update to that, we started to do some sea level rise modeling, the cost efficacy of building higher than required in the US. And what we found is that was quite cost effective. And off the back of that, we kind of ended up with a pretty good coastal model. And on the basis of that, got this work with the country of Antigua to look at what might happen as the decades progress here for hurricane risk. So for those who aren't familiar with Antigua, it's a very small island in the Caribbean. It's home to Eric Clapton and Oprah Winfrey, a lot of very, very high-priced resorts and offshore banking. I'm not getting advancement here. Okay, so we had a pretty good team here. It was led by ImageCat. The hurricane modeling was done by Kinetic. We also worked with Scripps Willis, who had a lot of domain experience, obviously in the insurance field, and the Met Office in the UK to do our modeling. The modeling framework, typical sort of hazard, exposure, vulnerability as the basis. And from that, we calculated direct losses from surge and wind independently, downtime, and impacts to key industries. We did that for 3 scenarios, 3 building quality scenarios. One, as we deduced the building stock was on the island, the vulnerability as built. If another scenario where if everybody built to code, and the building stock was at code, and then one that was above code, which would be our sort of recommended approach to building buildings. And we did that for 4 different sort of loss scenarios, one looking at a maximum event that you would expect to hit the island, one for a historic event that hit the island for comparison, a 1% annual or 100-year event, and then we ran 1,500 scenarios and then took the average to get sort of an average annualized loss that would be expected. So we did that for 2020. That was about 120 modeling scenarios. Then we integrated in the climate conditioning, which would, based on the sea surface temperature and sea level rise, give us different profiles for surge and wind, and modeled 2 climate scenarios, what we call stabilization and high emissions. So that was a RCP 4.5 and 8.5, and modeled those on a decadal basis to the end of the century. And what we found when we got into it is that we had to take exposure out. or else you got results that were a little ridiculous. Every little wave would cause catastrophic damage because your baseline was that places were underwater. So what we did was model separately the exposure to sea level rise plus a 10% nuisance flooding event plus wave height, and took that as a sort of a different loss category, and then essentially took that exposure out of the equation. So the idea was once you're hit by sort of a 10% nuisance flooding event, you're not going to rebuild there and won't be vulnerable to a hurricane moving forward. So all of that was about 1,000 different scenarios here. Here's a sort of a sample of some of the things we produced. So on the upper left, you have the progression of losses anticipated from storm surge alone. So starting at around under 50 million and then going up to 2,100, looking at 125 for the RCP 8.5, and then only about 50 for 4.5. So that's just the surge. And then in the middle one, you've got the wind there quite a bit more. And on the right, you have normalized by the exposure. And again, since you're taking exposure out of the equation, that's non-linear, but that's what you can use to essentially set insurance rates. And then we produced tons of these maps to show where those losses would be for the various scenarios, which we put on a portal for them. And I can pass on to you guys. So more along the interests of this conference, here are the results from the nuisance flooding separate analysis that we did. So on the left, you've got the 4.5 RCP. On the right, you've got the 8.5 RCP. And as you can see, you've got a lot of exposure anticipated just to be susceptible to sea level rise and nuisance flooding and wave action alone. And we've broken that down. The color striations are feet above sea level and then the actual dollar amount. And so that feet above sea level is not only the rising sea, but the rising, on top of that, the 10% plus wave, which is essentially factor 1.5 on top of those two added together. So key observations from the analysis, the coastal properties were much more vulnerable as a percentage, and that's what, you've got a lot of resorts there, for example, but the most of the loss was actually for the island as a whole. So you have to have a sort of mixed mitigation strategy there, but higher elevations, building higher, raising structures, building a little farther back from the beach. People have to go a little farther to the beach. It's not the end of the world, but it's highly cost effective. The focus on resorts, some people say resorts, who cares what the hell? But fact is, the economy of the islands really depends on these resorts and people coming to visit there. So if those are all damaged, then people aren't going to be coming to the islands and spending money. And that's really what the jobs are based on. And then you would have migration and so forth. So really important to protect them as economic generators. And ports, getting things in and out for rebuilding, those port facilities appeared to be vulnerable as well, although we didn't look at them directly. And then there was some access issues as well. So we tried to really emphasize to them, we didn't go and do an engineering survey of any of the specific buildings. The future is unwritten. This is a large scale analysis and so forth, but this is appropriate to be used for adaptation strategies and further investigation of key assets. And there are follow-on studies to look at just that. The client was incredibly engaged, very, very sophisticated in terms of digestion of this information and really wanting to act on it. So that's my slide deck. This is, it's a very sophisticated approach to climate condition, existing CAP models, and look forward into the future as to what might happen. This is not something that insurers are bullish on. They renew their contracts every year. So what happens in 2050 doesn't necessarily impact them directly. They're being pressured to do so. So they're looking at it more and more. But it's something that is sort of low-hanging fruit that's out there for us to grab and do for a country like the US, where we can start to use that to prioritize their own managed retreat strategies. All right, that's what I got, Alex.
Thank you, Charlie. And this is really a nice way of closing because it kind of closes a circle. We had a couple presentations that were more academic in nature and kind of giving a broad view of issues around the coastal zone and what may happen, flood risk, heat risk. We had one, my own, that was kind of more aimed at government audiences, and then this, which is really both private sector and public sector. I'd like to invite all the panelists to come back on with their cameras on, and we do have a few minutes to entertain some of the questions that were put in the chat. I'm going to start with the first one in the chat. Maybe you saw it, Cascade, but I will repeat it for the benefit of the broader audience, which is, do you have a hypothesis for what drives places having increased exposure primarily due to population versus urban warming? I would think these would be correlated because of the urban heat island effect. You expect to see, obviously, more people in urban areas. So Cascade, over to you.
Thanks, Alex. Yeah, that's a wonderful question and one that is really important to this research. And I apologize for getting the Q&A in the chat confused, but I did a little bit of a response. But in a sense, you can think of exposure as three things. You have population, you have the urban heat island effect, and then you have climate forcing agents. My study lumps urban heat island and climate forcing agents into one urban temperature signal. So yes, in general, there should be a correlation between an increasing urban heat island effect and population growth. However, that pattern too, we think, is highly spatially heterogeneous, and that's paper number 2. And if anyone has more questions, I would love to follow up because we have a couple different ideas at how to get at that question to separate the signals between climate and urban heat island effect. But it can be challenging. So yeah, it's a great question, and I really appreciate it. Thank you.
Thanks. So Beth, am I freezing? Is Beth frozen? There she is.
Yeah, no, I'm here. I hear you going in and out. So say your question, but I might need you to type it. Or usually I can put enough of the pieces together, but.
Oh, I'm sorry. I think it's an internet issue on my end.
I think so.
83% accuracy. How did you get?
Oh yeah, so I answered that in the Q&A, but when I say accuracy, I mean the ability of our algorithm to correctly identify water and MODIS imagery. That's like a pretty important caveat because that's different than saying, did we correctly identify maximum peak flood extent? I don't know. I'm sure we underestimated by quite a bit. We don't actually have the data unless we had high watermarks to know, the difference between the satellite overcast time and where the water might have receded. So again, this is accuracy of our correct classification of the MODIS imagery, not of maximum peak flood extent. So with that caveat, it's a pretty classic remote sensing accuracy assessment where you try to get another higher resolution imagery that's image at the same time as your lower resolution image. In this case, we used Landsat, which is 30 meters because MODIS is 250. We randomly stratified points over every Landsat image that overlapped basically the peak flood day in the MODIS image that was cloud-free enough that we could put points. We did over 30,000 points, and then we stratified based on 25% of the points being in dry land to try to sort of pick up on, potential false positives, 25% in permanent water, which we better get right, and The other half of those points, we basically tried to sample along rivers and coasts where we thought the flooding probably would be, so that we could like get a really challenging set of points to identify. So an analyst will look at the Landsat image and the MODIS, or not the MODIS image, just the Landsat image, and say, is this point flooded or not? And then we compare that to our classification. So it's a classification overall accuracy of total correct divided by total number of points. And the variance is about 15%. So some maps are better than others by a lot.
Thank you, Beth.
There's
a quick
Alex,
question from me. Yeah,
Alex,
go ahead, Kit.
could I just comment quickly? I think that, as a community, this term accuracy is something that it's really our obligation to educate policymakers about what we mean when we say accuracy. We don't want people to get the wrong impression that we're talking about ground truth when we may or may not have that information. So I see this again and again across different communities, but especially here when we're talking about flood data, that if a policymaker hears accurate, they might have a different definition of that than we would as a scientist. So I just wanted to get on my soapbox for a second on that.
That's a really good point. I actually think in remote sensing, we give ourselves too much credit for accuracy, and that often the way someone experiences sort of a map and decision making on the ground is really different from these sort of random stratified points that we sample. So kind of, I think we need to think about that much, much deeper. I totally agree with you.
Just add that the paper that just came out in Science about really mixing these big top-down modeling, which are wonderful and exciting, with bottom-up actual on the ground.
I think Cascade cut out.
I'm not sure if it was me or...
We lost you at mixing top down with bottom up on the ground, and then you froze. And can you say what paper you're listening to?
Hopefully my internet's back. Alex, I believe Alex is an author on the paper, so Alex can say the title, but it just highlights the need that in these big remote sensing studies, it's so important to work with bottom-up approaches with social scientists, with policymakers, to really get a holistic picture. And I think there's a lot of
So we may be experiencing some of the inevitable internet issues. I want to just leave it open for any last comments. There are a number of comments in the chat, things that came through. I don't believe, Charlie, your responses are visible to the people outside of our little bubble here. So if you want to say a word or two about how you did the climate conditioning of what the question was basically on, how you climate condition the wind and sea level, especially the wind.
Oh no, sorry about that. Yeah, so climate conditioning was directly correlated with sea surface temperature. I can't remember the paper that we based that on, but the guys at Climate Tech gave us a fancy equation where, based on the increase in sea surface temperature, we increased the wind. Based on the increase in wind, the surge was higher, and then the sea level rise was added on to the surge from there. There's a couple great questions about the involvement of Antigua. Yes, Antigua was the client, the Department of the Environment there. They were very concerned about the environment and the natural resources, both intrinsically and because of the importance of it as an economic asset. So that really informed a lot of what we did. There was a propensity for them to feel as if they could use the results directly for decision making, which we really emphasized that has to be integrated with an additional evaluation of possible solutions and community involvement. And they did, to their credit, listen to that. And we did have follow-up meetings and projects to basically involve the community to try to figure out what to do. I think that probably the most obvious thing that they're going to be doing is to harden those coastal facilities.
Great. I actually had one last question for you and Andrew, and it really relates to the degree to which agent-based modeling, I know it's used in a variety of business settings, but have either of you seen ABMs used for specifically climate risk analysis, population exposure, population migration, things like that in a kind of business context? I'm just curious.
We've used it in transportation modeling and evacuation modeling. We have not used it for any sort of climate stuff directly. It's not, I would say that some of the insurers talk about it, but it's not seen as, you know, it's sort of your assumptions a priori impact what comes out of it. And when you're making financial decisions and have regulators breathing down your back, you got to be pretty careful. So you don't see it as much as you do in academia, I think.
Yeah, I mean, the following the challenge is that there are applications where secondary data work for you and you're able to calibrate your model to some outcome. But to any extent where you're really interested in how individuals perceive things differently or make decisions differently, then you get into the need to collect data and understand people. And it's just not very scalable. It's expensive. And so I think that's probably why you don't see it used as much in that context.
Great. Well, I'm glad we did have a little time to talk at the end. I wish there were more time, but this has been really a very rich session. I think it's certainly one of the highlights for me of this conference. So with that, I think we'll close this session and thank again the speakers. And this will all be recorded and you can look at it at your leisure later. Thank you.
Yeah, thanks, Alex. Good job.
Bye now.
Yep.
Thank you, everyone.